Abramo Hefez starts on the topology of polars of analytic related branches.
I wish to thank the invitation by expressing my happiness of being here at such a nice meeting in honor of Pepe Seade. This work is dedicated to Pepe Seade on occasion of his 60th birthday. So our final goal in this project, this was a project, was to describe the variation of the topology of the polar curve associated to a germ of a reducible plane curve belonging to a given singularity class. I wish to bring you some global results, some general results, but unfortunately I can talk about the strategy to solve some local problems. In the last talk I gave on this subject 2 years ago, we were more optimistic about this program, but it turned out to be a difficult problem, since the topology of the polar curve depends sensibly on the analytic type of the curve and not on some other coarser attribute. So it's very sensitive topology of the polar. So now it seems hopeless to expect to solve this problem in general, but we will show the strategy we use to solve it completely in concrete instances. Well, we start with f power series in 2 variables with complex coefficients such that it vanishes at the origin, and we denote by f in parentheses the zero-set germ of f in 0, the neighborhood of 0 of C2. Since the concept of polar of a curve is somewhat subtle, because it depends on the equation of the curve, we start by seeing how it behaves under some natural equivalence relations to be considered. So the first one is the associative relation, for which f and g are equivalent if there exists a unit u in C of xy such that g is u times f. Well, when f and g are reduced, then one has that the curve defined by f is equal to the curve divided by g if and only if f and g are associated. There are equivalents or analytic change of coordinates at the source for which f is r equivalent to g if there exists an analytic local isomorphism phi, the neighborhood of the origin of C2, such that g is equal to f composed with phi. So as a combination of the associative relation with R equivalence relation, we get the K equivalence for which f is K equivalent to g if there exists a local analytic isomorphism phi and a unit u such that g is u times the composition of f is phi. So you change coordinates, analytic coordinates, and then you multiply the unit. The K equivalence on functions vanishing at the origin induces an equivalence relation among germs of curves called the analytic equivalence, defined as follows. The curve defined by f is analytically equivalent to the curve defined by g if and only if the equations are K equivalent. Then the topological equivalence or equisingularity in which analytic equivalence is relaxed in the following way. We say that f is equisingular to g curves if there exists a germ of homeomorphisms P, the origin, close to the origin of C2 and the unit such that G is U times F composed with V. So we allow homomorphic change of coordinates instead of analytic change of coordinates. So we use the following invariants to describe the equisingularity class of a germ of plane curve. There are several ways to express the equisingularity, but what we use is for a branch, its same group of values, which is the set of intersection numbers with intersection multiplicities of f with all power series which do not lie in the idea generated by f, which will be represented by its minimal set of generators. So this gamma is minimally generated by V0, T0, U1, G, where G is called the genus of the curve f and measures its topological complexity. For a reducible curve, the same group of its branches and the intersection multiplicity is among them. These are the characterization of equisingularity we use. Now go to polars. Given a function f, a polar of f is a member of the pencil of power series, which are a combination of the partial derivatives of f and with respect to x and y with constant coefficients. And what are the common properties of the elements in this linear system? Well, if f is reduced, then the general number of this linear system is reduced, and the curves associated with the two general elements in this pencil are equisingular. So we will call the general member Pf of this linear system the polar of f, and its equisingularity class the equisingularity class of the polar of f. So this is the general polar of f, which has a well-defined topology. The notion of polar doesn't make sense for a curve f, since a polar of uf, u times f, has no direct relationship with the polars of f. So one remark I would make is one could define the polar of f as a general member of the Turing ideal. In such case, the polar of f would be well defined because the polar the Turing ideal is the same for f and uf. And an important fact is that the topology of a general member of the Turing ideal is the same as the topology of Pf. Now, since Turing of f, the Turing ideal of f is equal to Turing ideal of uf, it follows that the general polar of f and of uf are equisingular. This allows to define the equisingularity class of the polar of the curve f. This notion of polar doesn't make sense for a curve f. Caution, one may not talk about the analytic type of the general polar of f because the analytic type of the polar of f with respect to a direction depends sensibly upon the direction. Only so far was for a fixed curve f. Now a natural question that one could ask is what happens to the topology of the polar when I say the polar of f is a general polar of f when f varies in a given equisingularity class. At an early stage of the theory, mathematicians thought that equisingular curves would have equisingular general polars. But this is not true, as one can see from the following simple example to find. This is the favorite example of everybody, the simplest one. So we consider the family f lambda of curves defined by y3 minus x11 plus lambda x8y. These curves are all equisingular with semi-group of values given by 3 and 11, minimal generators. The general polar curve, if F0, has two smooth branches intersecting with multiplicity 5, while the general polar of F lambda for lambda different from 0 has two smooth branches, but intersecting with multiplicity 7. So they are not equisynclinal. Okay. Well, there are two results that describe partially the topology of the polar for curves in a given equisingularity class of plane branches. The first one is the following theorem due to Mer, 1977. And the theorem says that if F is a germ of a reducible curve with semi-group of values, V0, V1, Vg, and we put Ni, these integers which are here, every work curves, which are the quotients of the GCDs of the generators, and we put N0 equal 1, then the generic polar PF of F decomposes into G packages, G equals to the genus of the curve, H1, H2, Hg, such that for each index Q, the multiplicity of HQ is given by this number, and each branch, so this HQ are curves composed with many branches, usually. They have only one branch, but usually they have lots of branches, and each branch of HQ satisfies this equality, the intersection number of the branch with F divided by the multiplicity of the branch is equal to this number, VQ over the product of these Ni's. Okay, this is a very beautiful result. And one cannot expect to get more information from the polar of all the members of an equisingularity class than this theorem says. Because what happens inside each package depends on the curve F and not only on its singularity class. So you have this rough decomposition, but inside each package you don't know what happens. The second conclusion, this one, in the theorem, and the classical contact formula say that the branches of HQ have genus at least Q minus 1. The second is a deep result obtained by Eduardo Casas Alvero in the 90s, and says that the topology of the polar of a general member of an equisingularity class is constant and is determined by a certain Enriquez diagram constructed from data of the singularity class. In the case of genus 1 singularity classes, the topology is much simpler to describe. The topology of the polar may be described in terms of the representation of the quotient of the generators of the semi-group in continuing fractions. This is a very beautiful result, and this comes in the direction of saying that, well, the classical mathematicians, well, they were correct, I said correct things generally. So generally what the mathematician thought is correct. The topology of the polar is constant, generally. Okay? It's a good exercise to describe explicitly Mer's packages for the general branch in the singularity class by means of these Enriquez diagrams of the polar. So by doing this, one can deduce some interesting things. For instance, all branches of the polar of a general member in any equisingularity class of genus G have genus G at most. Okay. So the general member of the equisingularity class, okay, its polar cannot have branches with genus greater than G. Recall that from Merle's result, the polar of any curve of genus G has at least one branch of genus greater or equal to G minus 1. There are very few equisingularity classes of branches of genus G such that the polars of their general members have no branches of genus G. You see that they have any member, any branch of the polar have genus at most G. Okay? But most of the equisingularity class, the curves have, the general curves have branches with genus G. So the ones that do not have a branch of genus G are very few and may be described explicitly. So for example, when G equals 2, there are two kinds of such equisingularity classes given by semigroups of the form QP, 2Q, 2PQ plus D. The people working with singularity of curves know this semigroup. And semigroups of the form EP, EQ, EPQ plus 1 with GCD, PQ equals 1. So there is some intersection between the two families. You see when E is equal to 2 and G equals 1, and etc. Okay? Equisingularity classes of the first kind are very interesting and have been studied by Loewe and Pfister in Composition Mathematics in 1990 in an attempt to construct their moduli spaces with respect to analytic equivalence. Okay? Now we are able to give the whole construction from these equisingularity classes. Or analytic classification. Okay, the topology of the polar of a general member of these equisingularity classes are completely described by the following. Here, the general polar PF of a general curve, you see this is just for the general member of the equisingularity class, has one branch with semigroup PQ, which is part of the truncation. It's a truncation of the truncation of the semigroup, genus 1. So we have to take off the GCD of two numbers, which is 2. Well, they have a branch with semigroup PQ, and the other branches are the branches of the general polar of the general member of the equisingularity class determined by semigroup PQ. So they have a branch with semigroup PQ, and the other branches are the polars of the branches of the polar of the semigroup determined by PQ. Well, the branch of this last polar may be described in terms of the continued fractions representation of P over Q. So we have an explicit description of the topology of the general polar of these equisingularity classes. And the intersection multiplicities between branches is very easy to compute. Well, a further step may be given by observing that if A is K equivalent to G, then the general member of the linear system LF is equisingular to the general member of the linear system G. So the topology of the polar of F is a discrete analytic invariant of the curve F. Hence, it makes sense to talk about the equisingularity classes of the general polars of the analytic classes of germs of plane curves. So, any analytic class of germs of plane curves, they have a well-determined topology of their polar. A natural thing to do in this context is to study the variation of this analytic invariant within a given equisingularity class of plane branches using the analytic classification of plane branches in the normal forms that we developed before. So to establish a program in this direction, let us report some facts. For any equisingularity class of plane branch determined by semigroup gamma, may be parameterized by constructible set E in C to the C minus V1. V1 is the second generator of the semigroup, minus 1, whose points are the coefficients of the Newton-Crusoe parametrization, given there, truncated of the conductor minus 1. C is the conductor of gamma, such that any element with the Pepe-Seade class is analytically equivalent to one with the Newton-Crusoe parametrization as above. This is what Zariski did in his book. So that the Corsican complete. But it was proved in a joint work with Hernandez that the parameter space E may be decomposed into a finite union of disjoint constructible sets, E1, ER, where on each EL, the set lambda L of values of scalar differentials on the corresponding curve, which is an analytic invariant of the curve, is fixed. And we consider E1 the general stratum, that is the only one which is dense in E. So there is always a general stratum. In each stratum EL, there is a normal form for its elements, which we describe below. First of all, we have to introduce the Zariski invariant of the curve. So in the set lambda L, which is the set of values of differentials on the curve belonging to the stratum EL, minus the semigroup of values gamma, if this set is not empty, then the number lambda, which is the minimum of this set shifted by V0, is an analytic invariant known as the Zariski invariant of the curve. Now, recall the normal forms theorem, which says that if C is a curve corresponding to a point in EL, then either C is analytically equivalent to a curve with parameterization TV0, which is a monomial curve, TV0, TV1, when the set lambda L minus gamma is empty, or to a curve with the parameterization of this form, see, where you have T lambda. This is a risky result. You can start after the second generator of the semigroup. You can start with this value lambda with a coefficient equal to 1. And then what we did is that we got a short parameterization on the stratum, where the summation is over all indices I greater than lambda and do not belong to the set lambda L minus V0. Moreover, two curves C with the parameterization as above and C prime with a similar parameterization, that is coefficients Cj prime, are analytically equivalent if and only if there exists a complex number zeta, so a root of unit, a very specific one, such that one has Cj is equal to this root of unity to the power j minus v1 times Cj prime. This means that you have, on these normal forms, you have the action of a finite group. And this gives you, the portion of that gives you the moduli space for the analytic equivalence. The question is the topology of the general polar constant in each stratum EL. This is a natural question to make, but this would be a dream. Unfortunately, as we will see later, the answer is no. If this was so, the problem was solved. But by using a dense Zariski set, whose elements have equisingular polars. This is very easy to get using the Ramanujan theorem, the constant. Part of Casas-Albiol's theorem, which says that generally the topology of the polar is constant, is the E1 part of the result. Bad news. Well, it seems to be out of reach in general to give an explicit description of the equisingularity classes of the polars of the elements in each stratum EL for L greater than 1, even for the general numbers of the stratum. A little comfort. If you give me an equisingularity class, then maybe after some work, I'll give you back the topology of the general polar of all of its members. This worked in all attempts we made, giving us a stock of examples. So for example, suppose you gave me the equisingularity class determined by the semigroup 512. I will tell you how are the general polars of all of its members. So the normal forms theorem together with the algorithms associated to it give us the following classification. So we have the full classification of this group. These are the normal forms. There are 18 normal forms which are related to the values of the set lambda. This is lambda L. So it doesn't make no difference if we take lambda L minus gamma, which is a finite set. It's easier to write. So we have here lambda L minus gamma, which are the values of non-exact differentials used by Zariski in this work. Okay. These are the values of non-exact differentials of the curves. The stratification is done by these values of non-exact differentials. Okay. So you have these 18 strata, and you can start, because if you don't have such a result, you have no hope to solve the problem. If I give you the equisingularity class 512, well, from where should you begin to work? So this is a good starting point. Okay? Any one of the curves in the family 1 to 9, and this is a very easy computation, has an irreducible general polar with semigroup for 11. So all the families 1 to 9 are completely classified from the point of view of the topology of their polars. So the polars of the curves in family 10 have two branches, one smooth and the other with semigroup 3, 8, with intersection multiplicity 8. So it determines the topology of the polar. Any one of the curves in the families 11 to 17 has a polar with two branches with semigroup 2, 5 with intersection multiplicity 10. Okay, and now comes the interesting stratum. The family 18 is the only one in which the equisingularity class of the polars will depend upon the parameters in EL to which it belongs. So the first 17 cases does not depend on the coefficients of the parameterization. These are absolute. Now, if C is equal to 1, then the polar has a branch P with semigroup 2, 5, and two non-singular branches, G1 and G2, such that intersection multiplicity of P with the GIs is 5 and the G1 with G2 is 3. So I'm giving this example to convince you that it's possible to get very explicit description of the polar if you use the random classification. So if C is different from 1 and different from minus 5 over 4, then the polar has two branches with semigroup 2, 5 and intersection multiplicity 10. Okay. Well, this is the interesting case. where when C is equal minus 5 over 4, and D is different from minus 5 over 16. That the polar is irreducible of genus 2. This is an exceptional behavior, because as we saw, in general, we could expect only branches of the polar with genus at most 1. And here we get a polar with a branch of genus 2 for a curve of genus 1. Okay? And if C is equal minus 5 over 4 and D is equal, so this is a special member of the family. The second line, when C is equal and D equal, then the polar has two branches with semigroup 2, 5 and with intersection multiplicity. So the remark is the stratum AE18 gives us an example in which the equisingularity class of the general polar of its members is not constant. So it may vary in the stratum EL. To also give us a somewhat unexpected at the beginning example of a family of curves of genus 1 such that its general member has a general polar of genus 2. Well, after we discovered this case, this pathology, we found that we could produce examples of branches of genus 1 whose polars have branches with arbitrarily high general. So this can be produced. Well, so we have the machinery, and once we have the classification of an equisingularity class, we can do the work and compute the polars. So I give you an example of how this could work. So I will give you an example. Previously, we had classified all branches of multiplicity less or equal than 4. Up to multiplicity 4, up to multiplicity 3, this was well known, as a Risky, Ebay, people. And for 4, very few cases were known. So we succeeded to classify all branches of multiplicity up to 4. So we have two cases. We have the case of genus 1, multiplicity 4, genus 1, and these are the normal forms. This table is very condensed, so you have lots of cases. It's condensed, it contains all the information you need about an analytic type of curves up to multiplicity 4. In this case of multiplicity 4. So you see you have 5 normal forms. And you have one normal form for genus 2, multiplicity 4 and genus 2. Like that. Okay, now the multiplicity for genus 1, with the first normal form, it was just this equation, y4 minus x to the n equals 0, it's a monomial curve, it's quasi-homogeneous. So its polar is given by that equation, and then it has GCD 3 and n minus 1, between 3 and n minus 1, smooth branches with mutual intersection given by this number. This is but the second normal form, you can get a complete table of the description of their polars. So this is a very good laboratory if you want to check some conjecture, or you have a lot of examples here of the whole description of the polars of all curves up to multiplicity 4. Okay, this is second normal form, and then you have the third to fifth normal form. The result is the same. Well, you have one case, one branch with semigroup 3m minus j, and in the second case, 3 smooth branches with network intersection number given by. And the other case is multiplicity 4 and genus 2. This is very simple case. The polar of any branch of genus 2 and multiplicity 4 has one branch with semigroup 2, V1 over 2, V1 is the second generator of semigroup, and one smooth branch with intersection multiplicity V1. So what we conclude from that is that it's very hard to get a general result about the topology of the polar. But what we feel is that if you give me a singularity class, after some work, maybe I could give you the whole classification, the whole description of the topology of the polars, of the elements of this singularity class.
Are there any questions from me?
As you say, to give a general answer looks very hard, but you already have very beautiful results, very interesting ones. I wonder to what extent those results, as a general philosophy, depend on the ambient space. In other words, if you consider, for example, rational double point in C3 and curves in it, you fix the ambient space and you study curves in it. I have a feeling that much of what you say can be done in that setting.
Yes. Well, what you can do is all the analytic invariants you may compute and they make sense and everything. But the analytic classification, I'm not sure to work. So we are having some trouble to generalize this for plane curves, not only branches. So the analytic classification for plane curves, well, it's a hard problem. We just solved it for 2 branches, and for more than 2 branches, it's a combinatorial problem, hard combinatorial problem. So if you go to the space, well, to start with, you don't have very good notions of singularity, and you have several notions, and well, the difficulties increase very much. But I'm sure that the invariants you can compute, they make sense. During a number, all these invariants, the values are differentials, we can compute them with the same algorithms.
Any other questions or comments? Okay, let's start the speakers.